Welcome everybody. Um, I am the lead developer of Atlas Engine, this project which is a 3D game engine, and this video acts kind of like a devlog where we come across the different things we make each month. So we're starting with February 2026. This was not the most productive month, you could say, but it was a productive month. We had 2 releases and we are going to see now what have we done. So let's begin by addressing numbers. And we begin with our community summary. So we have had commits from 2 contributors, 2 total stars, no issues, we hope that changes, and a total of 7 pull requests and 1 fork. And talking commits, we had commits to 4 branches with a total of 21 long-lived branches, and it was a total of 52 commits, and main is now 579 commits long, so that's very great. And now we're going to talk features. What are the features that we have implemented this month? So first we want to talk about the Vulkan problem, which was that we had incredibly harsh problems with the Vulkan pipeline we implemented with Opal 1 last release in Alpha 5. And it was really difficult to work with because the forward rendering worked, but deferred rendering didn't work, and so it was really hard to work with, and we had to rethink it. And the main kind of purpose to moving to Vulkan in the first place was that I, that work with macOS, OpenGL has a lot of limited support for macOS, and I wanted something that could really be powerful, mainly for the next release and the betas. So that's why you can see right in the bottom, we are moving to Metal 4. Not moving, but we are adding Opal. We are adding 2 Opal Metal 4, which is just amazing because it is fully complete. But also this moving, right, comes in very handy because I really had no Vulkan expertise at all, and it was really hard to work with Vulkan. And now Metal is really easy and helpful more than Vulkan, because I was already familiar with the Swift APIs, and just translating that to C++ couldn't hurt. And another thing is that we are moving from Make to Ninja. This is basically because I wanted to use CLion, but not just that, because Ninja is a lot faster. We had to force color outputs for some reason because they are not enabled by default. So we had a special compile flag for that. And we will solve problems with Clang Tidy to make sure our code base, which right now is a bit messy, kind of works better. Now, as I said, Metal 4 was also another thing that we implemented, which is as I already said, a new backend for Opal, which introduces with it Opal to Platonic, named so after the core Platonic solids, right? And it comes with new revisions to the Opal APIs besides Metal, which that's why we decided to make it a new release, and it introduces better support for macOS as well, since Metal 4 is very powerful, and especially with Alpha 7 that you'll see later, it will come really handy. And then general revisions, because we shadows were not working with Vulkan nor metal. So we fixed metal, we didn't fix Vulkan. Bloom was odd also with metal. And we did general library remakes as well. This was in a few days ago. That's why we introduced Alpha 6.1, because we wanted just to make some general revisions. And so this month we got Alpha 6, which comes with Atlas Tracer and its core, very useful. Atlas Tracer is an application, although I don't have an Apple developer account, so it's not signed. But it is both a protocol and an application for debugging Atlas. So you plug it in and you get object dumps, log dumps, and way more stuff. And yeah, now you have really cool, really working logging and debugging systems, which is just nice. And a new specification, a new PDF that we've made so that anyone really can implement their own Atlas Tracer client. And now, the most important part of this release, which is Jolt Physics. Why is the most important part of this release? Because it's amazing. So we are now running Jolt Physics 5.5.0, which is the newest, I think. And that introduces realistic rigid body physics and a new, better physics library and some helpers. So now you don't have to interoperate with Bezel anymore. You can just get Atlas physics.h to that for you. So we also made a component that you can attach to core objects, which makes things really easy. It integrates with Bezel Native and Bezel Jolt. So we have these two separated now libraries or build systems of some sort. Bezel Native and Bezel Jolt. So if you want to try Bezel Native, which I don't recommend doing it, you can. And also you can have Jolt, which is now kind of the mainstream thing until we implement our own. And so we also introduced vehicle and joint support thanks to Jolt, because this was the point we stopped in Bezel Native. So Bezel Native had basic rigid body physics and some quirk more, but joint support was really difficult, so we stopped there. And then fast multithreading, because that's Jolt. Jolt is fast, and with multithreading is double fast. And also Metal 4, as stated for the third time, with the C++ libraries, which offers better macOS integration. And then Alpha 6.1, which is the successor of Alpha 6, which basically included these general fixes. So it has a new, better API and solved linting issues. Not all, but we are working on that. A better CI on GitHub, that's really important. Our build system on GitHub has gotten really, really, really good. And yeah, this learning by creating thing. So when we were making the demos for this very presentation, we realized that there were things that we needed or things that were off, and that's how we basically came up with this release, right? Just staring at those files and thinking, hey, isn't there a better way to do this? That's basically the whole point of Alpha 6.1. And also this month in community. So let's take a look at community this month, because we now have a Discord server, which you can follow the invite link here. It will also be in the description. And this very YouTube channel. These are basically the new things in community. Next up, I wanted to talk about what to work in now. So what are we going to do next month? And the first thing is that we are going to center on CLI and build. This is our focus for this release. Well, I wouldn't say that. But CLI and build is something that is really fundamental to our engine, and we have to take care of it more because the CLI we have now is not good. We know it, and we want to do better. So yeah, just we have to do this better because we also have problems with the compiler and the libraries that we publish and it release, they are not cross-platform at all. And I just wanted to clarify that if you just go download the libraries now, they wouldn't work. They will not work except if you're running macOS, Tahoe, I guess, with the homebrew compiler. Because if you run it with the default compiler, it will say a mismatch error or something like that. So we want to work with that as well. And then Alpha 7, which is our next release, which will include, and I'm very excited to say this, Photon, which is our GI and ray tracing system. When I say ray tracing, I say path tracing, but it's just marketing, right? So Photon is going to be a thing that it's going to stay in our engine for a long time. We want to get this done right. And well, for those of you who don't know what global illumination is so when you have a scene, right? So the lights that are in that scene cast photons, and those photons kind of bounce around the scene, and that makes that, for instance, when you place a really red object in front of a white wall, it kind of generates some red pixels in the white wall because the light reflects. So that's global illumination, and global illumination would pair with deferred rendering. So you would have all the normal deferred rendering things, so SSAO, SSR, and GI. And then path tracing would be a totally separate thing because path tracing is incredibly accurate. But it also, the good thing about it is that it replaces everything. So you don't have to have, I don't know, light casters or shadow maps. All of that gets parsed by, or gets created by that path tracing thing. We're also going to introduce these previously mentioned CLI fixes and better pipeline design and materials. Better materials is a thing that we have wanted to implement for a long time, so, well, there you go. And well, we end this presentation now with a demo. We have a couple of demos to show you, so buckle up. Well, so the first demo over here is kind of a very simple game. That's why it's called Simple Game over here. And it is a game that is basically kind of a geometry dash thing, where you have a ball, and you have to jump through cubes, and if you run into a cube, then you die. Well, then you die. And so basically, it is really cool because we made the ball emissive, which means that it actually works, the mission thing. So it kind of was a test too. It looks great. And also with our custom procedurally generated skies, which fill the skybox really, really nice. With like different times of the day, it really, really is a good experience. So let me just launch it. So you can see over here we have this ball, and so now it's going to turn into night, and you can see that with raycasting I lost. Let me just launch that again, sorry. And that didn't mean to happen. I shouldn't have lost. But basically, Um, it really is a powerful thing. You see here the ambient light, right? How it goes really down, and you can still see the ball and everything. Whoa, that was very close. And well, it really is very nice. And I died. And you can see over here that this was really difficult to make because this is a scene change. And scene changes didn't work. So it was a pain getting them to work. But now they work. You can see it over here. So that's very nice. And then the other demo, which is ball. So you can see over here you can switch angles between the camera, and then when you push space, you drop balls. There's nothing more to it, but it's really cool. And well, you can see that I can drop more. This really pushes child physics to another level, but we notice an error when making this. If you take a look at the shadows, you will be able to see that they start to lose quality over time. And this is a problem that we have to fix, but basically just this. So imagine, well, this is a directional light, first of all. Directional lights are lights that just go in a direction. They don't have a position. Like the sun, for instance, the sun is a directional light. And this light casts shadows, okay? So basically, what we do to render shadows is we render the scene from the view of the light. So we just, like if you were watching from the light's origin to the scene. And what we do then is store in a depth buffer the depth of the image. What do I mean with the depth of the image? We mean, let me just adjust this. We mean with depth the distance between that origin and the pixel that it is being rendered. You can actually check that in your own project. If you uncode this display and instead use light shadow render target, because in the end is the render target, and you display that to the window, sorry, this is over. We make that again, you will be able to see that we have a depth image, which looks something like this. This is our pot, right? Since it's a directional light, it uses a perspective that it's called orthogonal, which means that it doesn't have depth. Well, it doesn't have depth. It is rendering depth, but it doesn't have depth. But the thing is the following. Let me just shoot a couple of balls. Did you see what happened? Did you see that it, for 1 second, it was made smaller? Why is that? This is because of a feature we have in our rendering engine. Because what happens is that directional lights basically focus all the world around them, and that's not viable for a game engine. You cannot have a texture, because this is a texture. You cannot have a texture that is endless. That wouldn't make any sense. So what we have is a limited texture, and we have an algorithm that checks for the position of objects, and depending on that, adjusts how much should the texture get from the world. I don't know if I explained that well, but you can see that when we click, it goes back because it detects, hey, an object is close, and then it pushes back for a second to make space to make that object fit in the target. But what's the problem of that? That is that if one ball falls, then it is going to get everything so tiny because we have lots of objects. And what that means is that the resolution of the original scene, which is what matters, is going tiny. So what can it what can be done to fix it? I think there is a technique which involves using the camera's perspective to do that. I don't know, but we definitely must look into that. Let me just rewrite that. And well, I just want to show you a bit the code behind this. So let's go to simple game 1 second and remove that. So the simple game was the platformer one. And you can see over here the structure, right? So the update function, this main scene. The update function, what basically does in this case is the camera. So it makes the camera follow the ball because you can see over here. Sorry if I moved that. You can see over here that if I open simple game, right, the camera follows the ball because the ball is moving. And well, that's what this code does. This generates a sphere and the platform and sets up the render target. And you can see the sphere has two components, which are the ball generator and the spike generator. So the ball generator is over here. Sorry, the ball behavior, not ball generator. And it basically does a couple of stuff. So it checks with the collision with spikes. It handles queries for raycasts, which you will see now the raycasting kind of logic. And then in the update, yes, we just say, okay, we want to raycast this. So we want to see if we are touching the ground, then set the linear velocity, the jump thing, and this is the logic for changing the scene. And now the spike generator just has a function to add this spike, which is done by a deck. Not a deck of cards, but this kind of deck, this kind of C++ deck. And then we have spike generator update, which basically spawns random spikes depending on the time. And finally, this is the end scene, which just has a camera. This is useless. And then some text. So here's some phone loading, some render target stuff. Pretty normal stuff. And then this is the code for ball pool, sorry. So over here, we got the definition for the objects that make up the pod. And then this is a problem here. Fixes there's some bug here. So this basically means that for some reason the first object you add to a compound object just disappears. So we have to create a copy. So there are actually 5 instances. Just that this one isn't showing because it is not initialized. But we gotta fix that. It showed up, but the position and rotation were not setting correctly. So yeah. And instancing is not supported yet, especially with physics, so we have to take a look at that as well. And in the main scene, we here chose to use unique pointers because we wanted to store the balls in the heap because then therefore we have more space. And well, this is a function to just generate the ball. And this update thing just switches between camera angles and it spawns balls. And in the initializing part, we just set the platform, water pot, the render target, and lights. Well, that's all. We will continue working on the engine, but yes, we there are lots of things that are still we have to do because we want this engine to kind of be good. But we don't have a very solid renderer. Now with GI and path tracing, it's going to be even more solid. And well, now the next step will be indeed to add UI, but that's going to come later. So, well, thanks for watching. I hope you stop by another time when we come up to YouTube next month. Thank you.